Welcome back. All right, now we're going to start using this idea about how we bring air parcels to saturation and how temperatures change in an adiabatic manner as we lift and lower air parcels to talk about a famous problem in meteorology. Every meteorology student at some point has to learn the so-called mountain problem. All the mountain problem is kind of a way of motivating moving air over a mountain. I mean, we want to find a way to, let me be more clear. We want to talk about reasons to lift and lower an air parcel. Okay, later in the semester we're going to find out there's lots of reasons to lift and lower air parcels, but right now a mountain is an easy one to think about. You have a windward side where the air approaches the mountain and has to rise to get over it, and you have a lee side of the mountain where the air sinks and then goes back on its merry way back at ground level. So you can see I made a happy little mountain there, you know, it gets white at the top and everything. I had a lot of fun drawing that in PowerPoint. Alright, so here is our mountain. We're going to ask what happens to a volume of air, an air parcel, as we move it over the mountain. So like in this particular case, I made my mountain be 4 kilometers tall. Any problems we do on the homework set or the quiz or in discussions will always be an integer number of kilometers so that we can just do this arithmetic easily with like subtraction and addition and so on. So we're going to start with an air parcel down there at 0 kilometers. We're going to lift it up on the windward side of the mountain to the top of the mountain, which in this case is 4 kilometers up, and then we're going to take it down the lee side of the mountain back to a height of 0 kilometers above the ground level. Alright, so here's my little air parcel. I'm just going to start it down there as a little blob down there at the bottom there. There's my air parcel at a height of 0 kilometers. In a mountain problem, you're always given the temperature and the dew point of the air parcel as it starts on the windward side. So here I gave us a temperature of 30 degrees Celsius and a dew point of 10 degrees Celsius. Now you can see I put a little key here on the diagram here that shows we're going to be moving the air parcel around, and as we do, the arrows will be telling us which lapse rate we're using here. You'll see how I did this in just a little bit. Alright, let's lift the air parcel 1 kilometer as it goes up the windward side of the mountain. Alright, from 0 kilometers to 1 kilometer, our air parcel is not saturated. I can tell because the temperature is greater than the dew point. Because the air, remember the dew point is the temperature to which we have to cool this air parcel to become saturated. So since the temperature is greater than the dew point, apparently this air parcel is not saturated. So you can see by the little black arrow there that I cooled the air parcel, using our key there, at the dry adiabatic lapse rate. So our air parcel rose 1 kilometer at the dry adiabatic lapse rate. So we have cooled this air parcel by 10 degrees Celsius. So notice now my temperature is 30 degrees minus 10 degrees equals 20 degrees. But notice the dew point didn't change. Why? Because remember, the dew point is just a measure of how much water vapor is in the air. We didn't do anything to change any water. We didn't have any condensation. There's no latent heat release. Nothing's going on. We didn't change the amount of water vapor in the air. So the dew point didn't change. But we have now successfully lifted the air parcel 1 kilometer. Let's do it again. Alright, at 1 kilometer to 2 kilometers. Again, my temperature is greater than my dew point. Therefore, my air parcel is not saturated, it is subsaturated. Therefore, we're going to lift it again by the dry adiabatic lapse rate. Again, you can see by that black arrow, I'm lifting it at a dry adiabatic lapse rate of 10 degrees Celsius per kilometer. So my temperature is going to decrease by 10 degrees. So I went from 20 degrees at 1 kilometer to 10 degrees Celsius at 2 kilometers. And again, because this is not, there's no saturation, we're not converting any water vapor into liquid water yet or anything like that, the air parcel that changes dew point. So at a height of 2 kilometers, we have a temperature of 10 degrees Celsius and a dew point of 10 degrees Celsius. Uh-oh. Something interesting happened at a height of 2 kilometers in this problem. At a height of 2 kilometers, we have now cooled the air parcel to the dew point. We have now cooled the air parcel to its saturation. In fact, there's a name for that. That is the lifted condensation level, the LCL. And the lifted condensation level is how high above the ground you need to lift the air parcel for it to become saturated. Remember, as we lift the air parcel, it always cools. As long as we lift it far enough, eventually it will have cooled to its dew point. That is the lifted condensation level. How high above the ground you have to lift the air parcel to become saturated. For most cases, this is where the height of the base of the cloud is. So from here on up, as we lift the air parcel any farther, it's a cloud. I mean, as we lift the air parcel farther up from here, we're making cloud, as I have badly illustrated here in PowerPoint. So from 2 kilometers to 3 kilometers, well, our air parcel is saturated. We are lifting the air parcel. It's continuing to expand. It's continuing to cool. But as we convert water vapor into liquid water droplets, that's condensation, which releases latent heat. We're using the moist adiabatic lapse rate instead of 6 degrees Celsius per kilometer. So from a height of 2 to a height of 3 kilometers, we cool at a rate of 6 degrees Celsius per kilometer. The temperature goes from 10 degrees at a height of 2 kilometers to 4 degrees at a height of 3 kilometers. What about the dew point? Well, the dew point's going to go down. Because remember, dew point is a measure of how much water vapor is in the air. And we're getting rid of some water vapor. We're converting water vapor into liquid water droplets. The water may or may not still be there. I mean, it depends on whether it's turning into rain and dumping it out. But there's less water vapor. That's no doubt. The dew point will now be equal to the air temperature. We have gotten rid of enough water vapor to change the dew point from 10 degrees Celsius at a height of 2 kilometers to a dew point of 4 degrees Celsius at 3 kilometers. Let me give you just a rule of thumb here. On the windward side of the mountain on a mountain problem, just keep the dew point equal to the temperature once you're at the lifted condensation level. So like now that we're above the lifted condensation level at 3 kilometers, go ahead and just keep the dew point equal to the air temperature. Okay, that's kind of a way to remember that, okay? Let's lift it another kilometer up. From 3 kilometers to 4 kilometers at the top of the mountain here. Well, we are clearly saturated. At 3 kilometers, the temperature is equal to 4 degrees Celsius, and so is the dew point. That air is saturated. We can continue to lift it, but once again, see the little blue arrow? We're cooling our air parcel at the moist adiabatic lapse rate. And as a consequence, we cool by 6 degrees Celsius. And we need to also reduce our dew point so that it stays equal to the air temperature by the time we get to the top of that layer. And we have made it to the top of the mountain in the mountain problem. Cool. We're halfway done. Now we got to come down the lee side of the mountain. Now on the lee side of the mountain, we're going to start with those conditions at the top of the mountain, namely that the temperature is 2 degrees Celsius and the dew point is 2 degrees Celsius. And we're going to start lowering the air parcel down the lee side. I'm sorry, the lee side. All right. Lowering an air parcel involves increasing its pressure. It involves warming. We're always going to be warming at the dry adiabatic lapse rate as we lower an air parcel. Because the temperature is increasing. We're only getting farther from saturation. We don't have to worry about any condensation or anything like that happening. So the air parcel will warm according to the dry adiabatic lapse rate of 10 degrees Celsius per kilometer. So as we go from 4 kilometers to 3 kilometers, our temperature is going to increase by 10 degrees Celsius. So we go from negative 2 degrees Celsius to 8 degrees Celsius. I may have misspoke before. The temperature at the top of the mountain was negative 2, not positive 2. All right, so negative 2 plus 10 is 8 degrees Celsius. What about the dew point? The dew point is not going to change because we're not doing anything to add or remove water vapor anymore, right? We are getting farther from being saturated. There's no condensation happening or anything like that. The dew point doesn't change. We can then go from 3 kilometers to 2 kilometers. Again, I can look at that and say temperature is equal to 8 degrees Celsius. The dew point is equal to negative 2. We are not saturated. This air parcel is not saturated. Therefore, we are warming. We're not changing the dew point. But we are increasing its temperature by 10 degrees Celsius per kilometer. So now we're at 18 degrees Celsius. And we can go down to another kilometer. And you can see the pattern here. We're not changing the dew point on the lee side because we're only getting farther from being saturated. There's no more condensation happening. And our temperature just keeps increasing by 10 degrees Celsius. So now we're at 28 degrees Celsius at 1 kilometer. And we can wrap up the problem by getting all the way back down to a height of 0 kilometers by increasing the temperature another 10 degrees. And then we end up at the base of the mountain on the lee side as having a temperature of 38 degrees Celsius and a dew point of negative 2. And we have completed this mountain problem. I could have chosen mountains of different heights. I could have chosen different temperatures. I could have chosen different dew points, but we could work it all through, and we will do a second one later in this part of the lecture here. But let's take a look at what we learned from this mountain problem here. Notice if we compare the conditions on the two sides of the mountain at the base. Notice that the temperature is higher on the lee side than it was on the windward side. Why? Lee side of the mountain is always going to be warmer when you do these problems. The windward side is always going to be cooler. Why? Because you got some heat into this. At first glance, you might have thought, lift it over the mountain and go back to the height you started, you should get the same temperature back. It will never work out that way, though, because as you lifted the air parcel, you got some latent heat out of the air parcel. You took some water vapor out of the air parcel and released that water vapor's latent heat into the air around it. You have warmed the air parcel. It is always warmer on the lee side of the mountain at the base than it was on the windward side. On the other hand, look at the dew point. On the windward side of the mountain, the dew point was 10 degrees Celsius. On the lee side of the mountain, the dew point is negative 2 degrees Celsius. Dew point, remember, is a measure of the amount of water vapor in the air. So apparently, the air on the lee side is drier, and the air on the windward side is more moist. It will always be that way. The lee side will always be drier, warmer, but drier. Why is it drier? Because we took some of the water vapor out of the air parcel as we lifted it over the windward side. We condensed some of the water vapor out in the form of liquid water droplets, which probably fell as rain on the windward side of the mountain or whatever. Oh, the air parcel on the lee side will always be warmer but drier. That is a phenomenon known as the rain shadow. If you look at this cross section across some mountains here, we're bringing some air at time 1 to the base of the mountain. As it goes up the mountain at like times 2 and times 3, you can see as we lift the air parcel, we're getting cooling and condensation and saturation. We get moisture. We're converting water vapor into liquid water, losing water vapor, but gaining that latent heat back into the air parcel. That latent heat is again becoming sensible, to use the correct term. Then you go over the top of the mountain, and on the lee side of the mountain, the air parcel is warming dry adiabatically, and when you get to the downwind back onto the base of the mountain, you are where the air parcel is definitely warmer, but definitely drier, the so-called rain shadow. The lee side of mountains are always drier than the windward side. A classic example of that is the state of Washington. The top diagram here is the topography of the state of Washington, and what I have labeled, you can see the green is lower and the browns are higher, okay? And I've labeled with that black line there the axis of the mountains there. I can't remember if that's the Cascades or the Olympic. I think that's the Cascades. Anyway, that's where the ridge of the mountains are. Wind comes from the Pacific Ocean on the left side of the diagram, goes up the windward side of the mountain, reaches the peak, which is that black line, and then comes down in the lee side of the mountain. The bottom diagram here is average annual rainfall in Washington. And look how I've superimposed that axis there, that black line right there. Notice on the windward side of the mountain, they have very high rain rates. Let's see, that's in inches per year. Like the purple colors there are like 100, 140, 160 inches of rain per year. Then you get over across the peak of the mountains onto the lee side, you're into the rain shadow. There's, that red is less than 10 inches of rain per year. Okay. See how they get much less rain on the lee side than they do on the windward side? By the way, the same is broadly true of the United States in general. If you think about like the Rocky Mountains. In general, on the lee side of the Rocky Mountains, as weather systems move from the west to the east, you can see how like it's much drier in, say, western Nebraska, central Nebraska, and so on, than it was like, for example, near San Francisco or western Oregon or in western Washington State or whatever. Nebraska, South Dakota, Kansas. We are in the rain shadow of the Rocky Mountains. Cool. Another thing I want you to notice on this diagram here is how the air on the lee side of the mountain was very warm as it was sinking. It was warmer always on the lee side of the mountain than it was on the windward side of the mountain. That is an important phenomenon in meteorology called a chinook. A chinook is a warm, dry wind moving down the lee side of the mountain. Let me give you that definition again. It is a warm, dry wind descending the lee side of a mountain. Anytime you have air flowing over a mountain on the lee side, you're going to have chinooks. And chinooks are relatively warm and relatively dry, and if you run a ski resort, you hate them. Because you only make money at your ski resort in the winter if there is snow. Well, when you have air flowing over the mountain, if you are on the lee side of the mountain, where the air is sinking, warm, dry winds are getting rid of your snow, and you aren't making any money anymore. This is a common problem for ski resorts. They have to be very careful as to where they build them so that in general they are on the windward side of the mountain and they get a lot of natural snow. They don't have to spend a lot of money making artificial snow. And they don't have to deal with days that there's not much skiing going on because of Chinooks. Okay, some of the world's greatest temperature changes ever have happened due to Chinooks. In fact, Spearfish, South Dakota has the world's greatest 2-minute temperature change. It warmed something like 75 degrees or something like that in 2 minutes as a Chinook moved in. And of course, any snowfall that was on the ground, snowpack or whatever, melted very quickly under that condition. Alright, before we end this lecture, I want to work through a second example of a mountain problem just to make sure that we're all clear about this. And rather than build it one slide at a time like we did before, I just kind of put the summary all up here. Let's say we started on the windward side of the mountain with a height of 0 kilometers, of course, a temperature of 38 degrees Celsius and a dew point of 8 degrees Celsius, okay? Clearly the air is not saturated because the temperature of the air is greater than the dew point. We have not yet cooled the air to the temperature at which it is saturated. Therefore, according to our key here, we are lifting our air parcel dry adiabatically from 0 kilometers to 1 kilometer. Therefore, we decrease the temperature by the dry adiabatic lapse rate, or 10 degrees Celsius per kilometer. So the temperature goes from 38 degrees at 0 kilometers to 28 degrees at 1 kilometer. And you'll notice we haven't made any changes to the dew point because we aren't condensing any water vapor out, and dew point is just a measure of how much water vapor there is in that air parcel. Great. Okay, how about 1 kilometer to 2 kilometer? At 1 kilometer, the air parcel is clearly not saturated, so we cool it at the dry adiabatic lapse rate. We change the temperature from 28 degrees at 1 kilometer to 18 degrees at 2 kilometers, and again we don't change the dew point because we aren't condensing any water vapor into liquid water droplets yet. Great, we're at 2 kilometers now. How about from 2 kilometers to 3 kilometers? At 2 kilometers, clearly the air parcel is not saturated because the temperature is greater than the dew point. Therefore, as we lift the air parcel, it will be cooling at the dry adiabatic lapse rate. So from 2 kilometers to 3 kilometers, we cool at a rate of 10 degrees Celsius per kilometer, and we end up at 3 kilometers with a temperature of 8 degrees Celsius and a dew point of 8 degrees Celsius in this case. And notice that the temperature is now equal to the dew point. Therefore, we have reached the lifted condensation level. This is going to be the height of the base of a cloud. You'll notice, by the way, in these mountain problems, we always set them up in such a way that it's all integers, and the temperature is never 28.3, and we never have like the lifted condensation level at 3.1 kilometers or something. In the real world, that would be how it is, and if you were an atmospheric science major or something like that, you'd be learning how to solve those kind of problems, but that's not where we're going with it in ATS 113. So in this case, our base of our clouds, as illustrated on this PowerPoint by that cloud clip art there, is at the lifted condensation level of 3 kilometers. From here on up, well, in this problem, I kept the mountain at 4 kilometers. So we're going to the top of the mountain. Well, we're going to be cooling at the moist adiabatic lapse rate of 6 degrees Celsius per kilometer. So our temperature decreased by 6 degrees. 8 minus 6 is 2 degrees Celsius for its temperature. And the dew point is going to change because we're changing water vapor into liquid water droplets in the cloud. Therefore, we are going to have a dew point that stays equal to the air temperature, because the air parcel is still saturated. So now our dew point at the top of the mountain is 2 degrees Celsius. We've got half the mountain problem done. Time to come down the lee side. The lee side is the easy part. Heck, let's kind of cheat. Let's do it the easiest way possible. We know as we lower the air parcel down the lee side of the mountain, the temperature is going to increase. And as the temperature gets warmer and warmer, is there any saturation? No, it's getting farther from being saturated, right? As we increase the temperature, the air parcel can hold more and more water vapor. It's not going to be condensing any water vapor out. Therefore, from the top of the mountain down, go ahead and just keep the dew point the same. 2 degrees, 2 degrees, 2 degrees, all the way down to the bottom of the mountain. That's fine. Okay, so we know at the bottom of the mountain our dew point is going to be 2 degrees Celsius. And then as we go down the mountain, the temperature will be increasing at the dry adiabatic lapse rate of 10 degrees Celsius per kilometer. So go ahead and just make it, okay, we know at the top of the mountain it was 2 degrees Celsius. Then just come down, 2 plus 10 is 12, plus 10 is 22, plus 10 is 32, plus 10 is 42, and we're done. Okay, it really isn't exactly rocket science once you see the pattern to the whole thing. But it's always best to check to make sure that you at least have an answer that makes sense. Remember, the lee side of the mountain should be warmer and drier. Well, the lee side of the mountain is about 4 degrees Celsius warmer than the windward side was. Good. And the dew point is about 6 degrees Celsius lower than it was on the windward side. Great. It is warmer and it is drier on the lee side, so I think we can congratulate ourselves that we solved another mountain problem just fine. Cool. The mountain problem wouldn't always have to be 4 kilometers. It wouldn't always have to start with these same temperatures. There's an almost unlimited number of combinations we could choose to make different problems in the homework or the discussion or the quizzes or whatever. This business of the lifted condensation level being the base of clouds is actually quite interesting. I mean, on an ordinary day when you just look outside at puffy cumulus clouds floating by, we'll learn more about types of clouds in a little bit. Most of these clouds kind of have a flat bottom. That flat bottom is the lifted condensation level. When you see these kind of low-level cumulus clouds out there like this on a sunny day, what's happening is air parcels near the surface are rising. They first rise at the dry adiabatic lapse rate because they're not saturated, but at some point they become saturated. The temperature of the air parcel will have cooled enough that now the temperature is equal to the dew point of the air. That's the lifted condensation level. That is the bottoms of these clouds. Then, as you lift the air parcel farther, you are creating an air parcel that is supersaturated. We have to quickly change water vapor in the air parcel into liquid water droplets that makes the cloud that you can see with your eye. Hey, this term MALR, moist adiabatic lapse rate, is a little bit uncomfortable. Your book slips up a few times and says wet adiabatic lapse rate. And I think once this book or else the lab manual slips up and calls it the saturated adiabatic lapse rate. Okay, if you're an atmospheric science major, you're going to see that there's actually, those are 3 slightly different things. Moist adiabatic lapse rate is not exactly the same as the wet adiabatic lapse rate. Don't worry about it, okay? In this class, there's the dry adiabatic lapse rate, and then there's the one that involves saturated conditions. And if the book slips up and calls it wet adiabatic or slips up and calls it saturated adiabatic, don't worry about that, okay? It's the same as moist adiabatic lapse rate. More or less all clouds form due to rising motion, which makes sense. If the best way to get saturated conditions in an air parcel is to cool the air parcel, and we know we can fairly easily cool an air parcel just by lifting it, looks like clouds are generally going to be associated with rising motion. Okay, no clouds are caused by sinking motion in the atmosphere, but there are other ways to get the air parcel to be cool enough that you have saturation. But 99 times out of 100, if you see a cloud up there in the atmosphere, it means that there is either rising motion going on right now, or there just recently was rising motion and it recently stopped. Okay, very few exceptions to that rule. That'll be helpful to you when we're learning about clouds in the next lecture. Actually, I think it's 2 lectures from now. All right, just to review. To make an air parcel saturated, which we're going to want to do if we're going to have clouds and rain and snow and fog and all the kind of good stuff that we think of as weather, we're going to either need to make the air parcel saturated by adding moisture, which that would be moisturization, that's fine, not a particularly great way to do it, or by decreasing the temperature of the air parcel so that the amount of water vapor the air parcel can hold has decreased enough that what it's got is all it can hold. Okay, we can make the air parcel saturated by decreasing the temperature, and it turns out there's broadly 2 ways to do that. There are the diabatic ways and the adiabatic ways. The diabatic ways are things like radiation and conduction and advection and so on, where you're actually removing and adding heat to the air parcel. Or there's the adiabatic ways, which are primarily accomplished through vertical motions and the resulting compression and expansion of the air parcel as you have vertical motion in the air parcel. Cool. This is going to be very useful for us for understanding different types of clouds and how precipitation happens and so on, the kind of things that happen in the rest of this module. All right, now as we wrap up what turned out to be a rather long lecture, let's answer 3 quick questions. Question 7. A rising air parcel reaches saturation at the blank on the blank side of the mountain. So is it the base of the mountain or the lifted condensation level? And is it on the windward side or the lee side? You can see you have all 4 combinations there. Okay. Make a choice from those 4 options and get a little feedback before you move on to question 8.